So, dear students, the topic for today will be potential energy in an external field. So, what you have here is you have some external electric field. Let us take uniform external electric field this way. Now, what you have to calculate here is suppose you have a charge, some charge Q on this external electric field somewhere at this point. Now what we have to calculate is the potential energy of this charge in this external field. So what will be the potential energy of this charge in this external field? That is what we are going to calculate. So to do this, what you have to know is you have to know that every point of an external electric field, suppose this is a point A, this is a point B, so in every point on an external electric field has its potential on its own. So it has predefined electrostatic potential for its own. Suppose point A in an external electric field have a potential VA at that point. External electric field at point B have VB potential at that point. Similarly, for this charge Q, at this point, you have some potential VR already at this point. So VR is the electric potential at point Q, which is already there. So what you are doing here is actually you are calculating the electrostatic potential for this charge. So this is nothing but it is the work done in taking this charge from infinity to this point. So if you bring this charge Q from infinity to this very point here, then what is your total work? That is the potential energy. So if you bring this charge from infinity to this point Q, you have to do some work against this electric field, and at a very point on this point on the electric field, it has a electrostatic potential VR. That means the total work done in bringing the charge at that point will be your charge into potential at that point. So this is the total work done in bringing the charge at that very point. So this is nothing but this is the potential energy at that very point. So potential energy of any charge at any point on the electric field is given by this relation, U is equals to QVR. What if we have two system of charges? Potential energy of two charges, system of two charges in an external electric field. Now suppose you have an external electric field this way. This is the external electric field. Now as we know, at every point on this external electric field there will be a electrostatic potential predefined. Suppose at this point, very point, suppose this is some point, and suppose this is my another point. So here suppose it is VR1 is the electrostatic potential at this point, and VR2 is the electrostatic potential at this point. And let us take Q2 is the Q1 is the charge at this point, and Q2 is the charge at this point. So we have two charges, Q1 and Q2, at this point and this point, and Q1 charge is associated with VR1 potential and Q2 charge is associated with VR2 potential, and they are separated by, let us take R12 distance. Now what we have here is to calculate the potential energy of this system of two charges, which is separated by R12 distance. So what is the potential energy of Q1 and Q2 system of charges, which is separated by R12 distance? So it is nothing but, as I've told you, the potential energy is nothing but it is the work done in making this configuration itself. So if you make this configuration, you need to do some work to make this configuration. That work itself is the potential energy of the system. So let us make that configuration one by one by bringing the charges one by one. So as you know, you have electric field oriented along this direction, and I have considered 2 points. One point at which the potential is VR1, and another point whose potential is predefined as VR2. So at these 2 points you are bringing 2 charges from infinity one by one. So firstly you are bringing Q1 charge to this very point. So on doing so, you are bringing Q1 charge at VR1 point. So on doing so, you have to do some work. So work done will be your Q1 into VR1. Similarly, you will bring this Q2 charges at VR2 point. So work done 2 will be your Q2 into VR2, because you are bringing Q2 charges at VR2 potential, but you are bringing Q2 also in the presence of Q1, because Q1 already arrived before Q2. You brought Q1 before Q2. That means when you bring Q2 out here, Q1 already is present. So the total work done is also influenced by the presence of Q1, which is at a distance of R12. That means you need to do some work against this Q1 also. So that work is your 1 by 4 pi epsilon naught Q1 Q2 by R12. So this is the work done in bringing Q2 charges against in the presence of Q1. So this is your total work done. So net work done will be your W is equals to W1 plus W2, whereas W is equals to Q1 VR1 plus Q2 VR2 plus 1 by 4 pi epsilon 0 Q1 Q2 by R12. So this is the total work done in bringing the 2 charges at 2 different positions, or this is the total work done in making the configuration of 2 charges itself. So this is nothing but this itself is the potential energy of the system. So VR1 plus Q2 VR2 plus 1 by 4 pi epsilon 0 Q1 Q2 by R12 is the potential energy of the system of 2 charges. So what you did here is, first you brought Q1 in the presence of VR1. So you did Q1 VR1 work done. Then you brought Q2 at point VR2. So your work done will be Q VR2. But when you brought Q2 at this VR2 position, Q1 was already there. So you did work against this Q1, presence of Q1 also. So that work is this one. So net work done is the sum of these 3. Sum of these 2. And that total work done itself is the potential energy of the system. So this is it for today. Thank you.